helps to solve different problems appearing in real analysis. And today I will discuss one of them, how we can use residue theory to compute improper integrals. So first of all, let me remind you what improper integrals are. So if we go back to calculus, so how did we define definite integral? Definite integral of, let's say, for now, continuous function is an area under the curve, right? And in this case, we assume that area is finite, so our segment is finite, and our curve doesn't go to infinity anywhere. So we have this nice area. Improper integrals, there are two kinds. One function just goes to infinity at some point, maybe end point or in the middle point, and when the segment is infinite. So they can be transferred one to the other type. So let's talk about this type. So when we have a continuous function, but the area, the segment, is infinite. So we will be talking about semi-infinite first. Right, so how to compute this area? Obviously that if your function here is growing, then area would be growing, so you'll get infinity. So there is no way to get a finite number. The function must be kind of decreasing, approaching x-axis, for instance. In that case, there is hope that we will be able to get a finite answer. And so how do we define improper integral? If we see an integral from a finite number to infinity, let's say of a continuous function, then we understand it as a limit. So when we replace this infinity with some number r, and then we compute this integral, and then we compute the limit when r goes to infinity. And in this case, we can get either a finite number or infinity, right? If we are getting a finite number, then we say that the integral converges. If we are getting infinity, then the integral diverges. So let's look at a couple of examples that I believe are familiar from calculus, just for you to get back to business. So if we have this example, from 1 to infinity, 1 over x squared dx. So we use this definition. We write limit r to infinity, integral from 1 to r, 1 over x squared dx. And then it will be, we are finding antiderivative. Antiderivative would be negative 1 over x. And then the substitution will be from 1 to r. So, and then we will get limit r to infinity, negative 1 over r, and then it will be plus 1. Right? So, and then we compute the limit. This number goes to 0, and the whole limit will give us number 1. So in this case, integral converges. And let's look at another example. Example 2, when we have integral from 1 to infinity, 1 over x dx. We write the same definition. We will get limit r to infinity, integral from 1 to r, 1 over x dx, and that would be equal to limit r to infinity, ln absolute value of x, substitution from 1 to r, and then when we will get r, ln of r will be growing, so integral diverges. So it's going to infinity. So here we have a convergent integral. It's converges, right? So you probably remember that if you have expression of the form 1 over x to the p, then p must be greater than 1, then you'll get a convergent integral. So this was one example. Of course, similarly, we can put a number, finite number here, say b, and put negative infinity here. And then the integral would be defined in a similar form. So what if we have an integral where both limits go to infinity? So in this case, the proper treatment is as follows. We have to split this integral in such a way that each integral has only one infinity. Probably the most convenient point would be 0 in most of the cases, but you can take any finite point a and consider integral one integral where you replace the lower bound with a number, and then this number goes to negative infinity, and the other with a different number that goes to infinity. What is important here that these two numbers go to infinity independently. So if you have to have, for the convergence of this integral, you have to have both integral be convergent. So if this limit exists and this limit exists, then we say that integral from negative infinity to infinity converges. In some cases, it is convenient to talk about Cauchy's principal value. So for Cauchy's principal value, you replace both bounds with the same number, r, negative r, and r goes to infinities. So let me maybe illustrate with this example. Let's look at this example when you have function just x, right? What is the graph of this function? It looks like this, right? So this is y equal x, this is x, this is y-axis. And if we split it into two integrals according to this formula, we will obviously get infinity here. And at the same time, we will get infinity here. So this integral diverges in general. But if we are talking about principal value, in some applications it's good enough. So in that case, we will just look at these numbers from negative r and r, right? And each time, since this is an odd function, this area will be cancelling this area, so we will get 0, right? So for principal value, we will get a finite number for generally this integral diverges. And you can probably understand that if we have an odd function, all this area would be equal to that area. For an even function, since it is absolutely symmetric with respect to y-axis, right? If we are getting on one side a finite number, then we are getting on the other side a finite number and the same number. So here we can write that integral from 0 to infinity multiplied by 2 is equal to the integral from negative infinity to infinity, and since it will be convergent, and principal value or just integral will give us the same number. So now I'm done with reminding you what improper integral is. So now let's go back to our residue theory. Let's consider an example. So suppose you have to evaluate this integral, and this integral is an improper integral from negative infinity to infinity, and in addition it has an unknown parameter t. So t here is real parameter, and the whole setting is real, x is a real variable. So before starting any computations, you need to figure out whether or not your integral converges, right? If it doesn't, then that makes sense to waste your time. So let's look at the integrand. And if we evaluate its modulus, obviously e to the itx is less, its modulus less than 1, so this function would be less or equal to than 1 over 1 plus x squared, and we just reviewed an example when you have an integral 1 over x to the power p. If p is greater than 1, then your integral would be convergent. So this integral converges. So then what methods often work? So basically in the previous times it was an art to compute integrals using Cauchy's residue theorem. So in many cases what works is if you take your function and then you replace your function with a function of complex variables. So basically what happened? You extend your function into a complex plane. So this is our complex plane, right? And if you look at this function on the real axis, it will be exactly the function that you originally had. And then since we know that this integral converges, it means that we can think about principal value, right? Integral converges, so principal value would be giving us the right answer. So we can take an interval from negative r to r on the real axis. And then if we send r to infinity, then we will be getting what we have here. So first we take this segment, and then we want to choose a closed contour, right? Since when we're talking about Cauchy's residue theorem, we have to have a loop, and we say that the integral along this loop equals 2 pi times sum of residues of all singular points. So, and here if we look at this, we have two choices. We can, for example, if we go from negative r to r along this, one choice would be it's just to close this integral using this half circle, and another option would be using this half circle. And then in both cases, we can, in the first case, then we can look at this domain, and in the second case, we can look, so if we want to close it, I have to choose the other direction, right? So I will choose the other direction. Then here we can go around, and here we can go around. So this one we can call, say, gamma r plus, and this one we can call gamma r minus. So which one to choose? It depends on our function, on the parameter t. Since let's see what happens. If we take z to be x plus I y, then if we look at the modulus of e to the I t z, which is x plus I y, then here when we distribute it, it will be just oscillating part, so the modulus would be I times I negative I, so the modulus would be e to the negative t y, right? So the idea is how to choose which part of the circle to take. When we will write Cauchy's residue theorem, we will write integral along the loop. So we'll write integral along this part from negative r to r, plus, for instance, integral along this half of a circle, and then we can compute residues inside, and what we will be doing next, we will send r to infinity. right? So we originally were choosing r in such a way that all singularities of this function are finite singularities are inside this circle, and then we will be just pushing r to infinity. And what do we want to do? Then we want that integral along this half of a circle converges, right? Doesn't go to infinity. And then, depending on parameter t, we will have two cases, because we know that on this part of the circle, our variable y is positive. And if t is also positive, then we will have e to the negative some positive number. That term will be decreasing. But if we take this part of the circle, then y would be negative. And then if we want to get a decreasing function, then we have to have a negative value of t as well, right? So for these two cases, when t is positive and t is negative, I have to include 0 somewhere. When t is positive and t is negative, then we have to choose these contours differently. So now let's start with the first case, when t is positive. Okay, so t is positive, and we are choosing this contour gamma r plus. So I have rewrote it here. So this is gamma r plus. So now we are working with this contour. So if we want to use Cauchy's residue theorem, let's write it here. It will be, so integral along this loop, so integral from negative r to r. Here I wrote f of x dx because on the real axis it doesn't matter if you write z or if you write x, because imaginary part is 0 anyway, so it will be the same thing. When we are writing our function on the contour gamma r plus, it's off of the real axis, so we write here z, right? And the entire integral is equal to pi I times a sum of residues of our function f at all singular points. So what singular points do we have in the upper half of the plane? So obviously the singular points would be, this part doesn't have singularities, 1 plus x squared, so singularities that this function has are located at points I and negative I. Right, so here we have I, here we have negative I. If we are talking about contour gamma r plus, then the only singularity that is inside of this contour, this one, is I. Right, so we have to compute residue of our function f at point I. So let's compute the residue. Our function here at this point has pole of order 1, simple pole, and it has representation phi of z or psi of z that we discussed in the previous lecture. So to compute the residue, it will be phi evaluated at point I at our singular point over psi prime at point I. So phi of z here is e to the itz. You can see, right, this is our function f, and psi of z is 1 plus z squared, so phi we evaluate at point I will get e to the negative t, right, when we plug here I, and then we differentiate, we'll get 2z, and at point z equals I will get 2i. So the residue is equal to e to negative t over 2i. So we take this value and we plug it here, so we have 2 pi I, so it will be 2 pi I times e to the negative t divided by 2 i's. 2 i's and 2 i's are cancelling out, and then we have just pi e to the negative t. Right? So this step, which involves Cauchy's residue theorem, is done. So now let's see what we need to do. Look at this formula, right? So here in the right hand side we have a number. In the left hand side, so this number will not change when we send r to infinity, when we compute the limit. In the left hand side, when we send r to infinity, then here this integral will give us our original integral that we wanted to compute. And we will be able to succeed only in the case if this integral doesn't grow, if it's not infinity, if we are able to evaluate this integral. So in the next step, what we will do, we will evaluate this integral, and as soon as we are done, we will be done with our computations. Okay, so here I rewrote what we have for our contour, right? We have integral from negative r to r, integral plus integral ln gamma r equals pi e to the negative t, right? This we got from the residues. And now, as we said, we need to evaluate this integral. So we need to evaluate this integral. And let's look what we have here. First, let me remind you the triangle inequality, this version that we have discussed earlier. And second, we should notice that if we consider in the case when t is positive or equal to 0, then modulus of this is e to the negative yt, and when t is 0, we will get 1. If t would be increasing, and since y is positive, the whole thing will be decreasing, so it will be less or equal than 1. Right? So this is about the top of our function. And the bottom of our function, for the bottom we used the triangle inequality, so z squared plus 1 would be greater or equal than r squared. So why I replace z with r? Because z here lives on this arc, right, of radius r. And so it will be r squared minus 1, right? That's what we have here. And then the entire function, if we evaluate the entire function, that it would be less or equal than 1 over r squared minus 1, right? The top is 1, the bottom is this. And now we have to evaluate this integral, right? So it means we can pull out this number, and then we need to multiply by the length of the this arc, and the length of this arc is pi r. Right, so then we will get that this is less or equal than pi r and r squared minus 1. And then the question is, what happens if we r approaches infinity? If r approaches infinity, this whole thing would be this will be going to 0 as r approaches infinity. Right? And then let's go to this formula. So when we know when r approaches infinity, this will go to 0, and this will go to our original integral. So we will have that integral from negative infinity to infinity, e to the I tx over 1 plus x squared dx equals to pi e to the negative t. And this is in the case when t is non-negative. Right? So we finished the first case. Now let's consider the case when t is negative. So in this case, as before, modulus of e to the itz equals e to the negative yt, but now since t is negative, we cannot use this r in the upper half anymore, because if t is negative, then it will be, with this minus, it will be a positive number, and then if we multiply by another positive number, this term will be growing. So to have a decreasing term, we have to deal with the contour in the lower half of the plane. So now we have this contour from negative r to r, and here from r through gamma r minus. And then, of course, as before, we assume that r is a big number. For us, it doesn't important how big, as long as r is greater than 1. And similar was for the case we just considered. Why bigger than 1? Because our singular points were I and negative I, they must be inside. So all finite singularities must be inside. That's how big r should be. And so when you change r, we have homotopically changing contour, so this value of the integral stays. And what you can notice that here in the first case we had a positively oriented contour, right? Contour was straight counterclockwise. In this case, if I still want to use the segment from negative r to r, I have to go clockwise. If I go clockwise, and if I want to write Cauchy's residue theorem, then I have to add minus to my residue, right? So integral along this contour would be equal minus 2 pi I times the sum of residues. And in our case, it's just 1 point where we have to compute residue. So it will be negative 2 pi I residue of our function f at the point negative I, because negative I is the only point is inside. And you remember that when we compute integrals using residue theorem, what's important, which points are inside. The points that are outside, singular points that are outside, they do not play any role. Okay, and then similarly, we compute the residue, right? So we use the same formula, phi over psi, so phi and then derivative of psi, and then we plug negative I, we'll get this. And finally, here I have my Cauchy's residue theorem rewritten. If I plug value of the residue, we will get pi e to the t. And so this step, second step, is done, and now we have to move to the last step when we take the limit when r approaches 0. And again, when r is sent to, infinity. When r is sent to infinity, then this integral will give us the integral we want to compute. And what's left is to evaluate this integral. And since we were choosing contour carefully, so everything should work, and we will be able to evaluate this integral, but I will write the details regarding estimate of this integral. And so now to finish this computation, we will just repeat evaluation of this integral. So t is negative, so on gamma r minus we will have the same estimate. So it will be, so t is negative, y is negative, it will be less than 1. And using triangle inequality, we estimate the denominator similarly, so the whole function will have the same estimate, 1 over r squared minus 1. And for the integral, we just repeat, it would be function and times the length of this arc, pi r. And since we have r squared here, then when r goes to infinity, the whole thing will go to 0. And then in this formula, we will get original integral that we want to compute here. This will be vanishing, and the answer will be pi e to the t. This is for the case when t is negative. And if we combine both answers that we got for both cases, for positive and negative t, we will get this formula that our finite integral phi of t is pi e to the negative absolute value of t, since in the first case we got negative t. So that would be the answer. This example is done. So let's consider another example. I wrote the entire solution on the board, so you can see that this is really not that bad. Okay, so we need to evaluate this integral. Integral from 0 to infinity x squared over x squared plus 1 dx. So first let's notice that this is an even function. Right? Since this is an even function, it means that integral from 0 to infinity equals half of the integral from negative infinity to infinity. So we can write that this would be equal, so if this integral converges, then we can compute it as this integral, and this integral also would be convergent, so we can deal with principal value, and we know that it will be convergent, we'll get finite answer. So how do we know that it is convergent? Right, if you look at this function, you can see the numerator grows as x squared and denominator as x to the 6. So if you at infinity, your function will be decreasing as 1 at x to the 4th, right? So x squared here, x to the 6. If we cancel x, divide by x squared, we will see that. This is this behavior. And similarly, like in the previous example, instead of our function depending on real variable x, we consider its extension into the complex plane, so by replacing x with z. So this is our auxiliary function, which we will be computing. And then let's look at these singularities of this function. Obviously, the singularities, singular points will be when denominator equals 0, so we have z to the 6 plus 1 equals 0. It means to compute z, it will be 6th root from -1. And you remember from the beginning of the class, we are going to have 6 different values. And what are the values? We rewrite -1 in the form e to the pi I plus 2 pi I k, right? I'm just reminding you. And then we multiply it by 1/6. So we will get all 6 roots, and they will make a hexagon. Sorry. And so we are interested now only in the points that are in the upper half plane, because we are going to consider. Let's first compute the roots, right? If we put k equals 0, we will get just pi I over 6. K equals 1, we will get this root. K equals 2, we will get this root. And 3 of them are in the upper half of the plane, and 3 of them are in the lower half. Since we are interested only in the upper half, we will mark them here, and we will be computing integral from -r to r, and we will choose this arc, positive arc, to compute the integral. Then we will just write the residue theorem in a similar fashion, so integral from -r to r. I need to comment here that here we don't have roots or singular points on the x-axis. So if we have a singular point just laying exactly on the x-axis, we need to use more tricks to kind of go around these points. But this is the simplest case. So we write this residue theorem from -r to r integral plus integral along this circular arc, and that would be equal to pi I times residues at these points, C1, C sub 0, sorry, C sub 0, C1, and C2, and C2. And let's compute these residues. Since, again, our function has the form phi over psi, then we can compute residue at once at all of the points. So then it will be our function phi evaluated at the singular point. Let's call all of them ck, where k is 0, 1, and 2. So here it will be ck squared, and here we differentiate. Derivative would be 6z to the fifth, so it will be, when we plug ck, it will be 6ck to the fifth. And then here I'm computing the sum of residues. When we have C0 is this one, right? So we square it, and then we divide by 6, and this ck to the fifth, and we do it for other two points. And after the simplest computation, then here to get this one, we just rewrite this as 2 pi I over 6 minus 5 pi I over 6. And we will get negative pi I over 2. So 1/6 I just pulled out. So here is simple computation, which results in negative I over 6. And then finally, we need to compute 2 pi I times sum of residues. So we take this number, multiply by 2 pi I, and we will get pi over 3. Right? So in this formula, the right hand side now is computed pi over 3. And so here this formula is rewritten. This is the integral we are trying to compute, and that will be pi over 3 minus this integral. Right? So the only thing left is to evaluate this integral to make sure that it doesn't grow. So here I am computing exactly pretty similar evaluation that we did in the previous example. So the whole integral will be less or equal to pi r is length of this half of arc of a half a circle, and then here z laying on the circle, so it is replaced with r. Here we use triangle inequality in a similar fashion as we did in the previous example. So we have r to the 6 minus 1, and then we end up with pi r cubed over r to the 6 minus 1, and then we compute the limit, right, when r approaches infinity. And this limit would be 0 because the top is growing like r cubed and the bottom as r to the 6. So limit is 0. It means in this formula, if we go back to this formula and send r to infinity, we will get in the left hand side integral from negative infinity to infinity of our function. Here we have pi over 3, it doesn't depend on r, and this integral will vanish. So now we know that integral from negative infinity to infinity equals pi over 3, but we were asked to compute integral from 0 to infinity, which is 1/2 of this, and that would be pi over 6. So this is the end of this example. Of course, there are more advanced examples, so if you're interested, please read in the book. Thank you.